Okay, so in today's video, we are going to talk about the first model, which is the k nearest neighbor. So this is a very simple method. We are going to using this method to actually illustrate the cross validation. This is one of the most important concepts in the practical machine learning. And in fact, you're going to use this cross validation ideas as we mentioned as again in almost every problems. I mean, since I mean, so at most of time there will be some hyperparameter need to be tuned, and to select the best possible parameters, um, for these models, and this also give you some idea. Second. Okay, so we're going to talk about the first method, the k nearest neighbor. So k nearest neighbor is a very popular one that sometimes and usually works on the classifications, but sometimes also works on the regression as well. So this is the most simplest approach that for the classification. So the underlying idea is if you look like your neighbor, and you are going to assign the corresponding labels as the same as your neighbors, right? So this is basically come with something called compactness hypothesis. So that means if the distance between the examples is measured well enough, then the similar examples are much more likely to belong to the same class. So as I mentioned, this is more like formal definitions. Um, so to actually classify each sample for for the test set, and what we're going to do is as the following. So the first thing is we are going to calculate the distance to each of the samples in this training and a set. That could be very expensive because you actually need to calculate this pairwise distance for any two in this training set. And the second is you're going to select k samples from the training set with the minimum distance to them. So basically, you are going to exhaust all possible training set. In the meantime, you're going to pick top and the k nearest of them. So these are the k nearest you're going to pick. Then you are going to using these k nearest neighbors as your informations to say, the class of the test examples will be labeled by the most frequent classes among those k nearest neighbors. So in order to make sure there will be no ambiguity, so usually the k is being chosen as odd if we want to work with binary classifications. So this ensure we always have one specific classes 0 or 1 to be the most frequent one. So and also this is for the classification. It's very natural, can be extended to regression if we need it. So for example, on the third step, if we are not returning the class, we can also return in the number as well, which could be the mean of the target variable among those k nearest neighbors. So that means we are going to get those target variables and around these k nearest neighbors. I'm going to take mean of that. But of course, it has some problems. One of the biggest issue is the curse of dimensionalities. You probably have learned that in the machine learning courses. One of the things in k nearest neighbor is if the dimension of the t and the feature is super large, for example, thousands, 10,000s, then to find out the actual and the k nearest neighbors could be very expensive because of this high dimensional an issue. There's a lot of mathematical justification why this is very difficult but the focus of this courses of this topic right now is not, and it doesn't lie on this curse of dimensionality. I'm just like pitching out to say there's something like that. And also why this is important for K and K nearest neighbor. I mean, in a lot of cases, wait. I mean, so in a lot of cases, for example, in those competitions or realistic data set, we need some like baseline or starting point as a comparisons. So K nearest neighbor, which is the simplest possible methods in the classification problems, can actually serve a good starting point or baselines in a lot of cases. So that means if the K and a K nearest neighbor can like reach say 75% of accuracies, so you have something in your mind, and whatever the more complicated and how complicated models or how simple of the models, you should at least beat 75% because that's what the K nearest neighbors is getting. And otherwise, if you are getting like 60%, like 70%, it's not worthwhile of the effort. You are making your model overcomplicated. It could be the problem of the overfittings. So under this baseline, like value is very, very crucial and very, very important in a lot of applications. And also in Kagos, K nearest neighbor can be used to construct a lot of like, so meta features. So basically, it's the K nearest and the predictions as a, and it could be the input to other models. So I mean, this is quite common. Like in the thing is like it's very complicated. And and one of the things that we can think about is and sometimes yes, we're going to talk about that in one of the case study problems in the later of the courses. And also this K and the nearest neighbor method is very naturally will extend to the recommendation systems. We're going to talk about these recommendation systems later on the courses. I mean, this is, you can think about this is, you are going to give recommendations of certain stuff, could be a movie, could be a book, that is popular among this closed and the closest neighbors that we want to make recommendations. So this is very important, and sometimes is very effective for that kind of recommendation systems. So in practice and to approximate, for very large data set, we are usually not going to find exact K nearest neighbors. If the dimension is super large, if data point is super large as well, could be like millions or 10 millions, it is impossible to find exact K nearest neighbor because that could be too expensive. So usually what we are going to use is something like approximate methods to do and to find and that kind of search. It actually, for example, there are a bunch of and open source libraries. Even with the scikit-learn has a very good libraries to work on the K nearest neighbor. There are multiple methods actually can find the K nearest neighbors efficiently. One is called local sensitive hashing. If you guys are interested, there will be complete separate courses where we'll be talking about these kind of stuff. But if you're not interested on these kind of stuff, so you can treat this like a lot of ways. If you and the data is super large, the K nearest neighbor is usually not exact. It's just like some good approximation to it. Also, the quality of this K nearest neighbor actually depends on bunch of parameters. Even with the K nearest neighbor, that simple problems, they also have some hyperparameter need to be tuned. For example, and of course, the most important one is the number of the neighbors, right? And whether we're taking one neighbor, 3 neighbor, 5 neighbor, and so on, right? So this is very important. And also, what kind of distance you're going to use, right? So you think about it could be Euclidean distance, between the 2 point, but sometimes Euclidean distance is not a good idea. So, and what we can using is something called cosine similarity. I mean, that's a very popular one. L1 norm, I know is also another one. And also, if we're talking about discrete sequences, Hamming distance will be very popular as well. Um, and most of these metric, as I said before, and require data to be scaled, because think about I mean, like we are comparing, for example, salary and the age. Salary is usually the order of thousands, and age is usually generally less than 100. So these two features are in different scales. If like and the feature are in the different scales that indicate we cannot just using k nearest neighbors directly. If we're using k nearest neighbor directly, we're emphasizing this features has a large order and a rather than small orders. So if we just using this k nearest neighbor for just two and these two features, hypothetically we are just using the salary features. So that's why we need to normalize that. And I want to remind you what is normalization or feature transformation. This is being taught in the previous lectures. And also the weight of neighbors. So this is also very interesting. So for example, usually, if we take so on the step 3, when we make the predictions for either class or whatever and regression problems that we have, we and hypothetically we are treating everything in terms like each neighbor has the same weight. But this might not be the super effective, but we can and actually assign the weight and the neighbors with a different weight. For example, the further of the examples that we're interested, the lower of the weight. So basically it could be 1 over and 1 over the distances. That could be the weight. Okay, so this is also very important. I mean, this whole thing actually being used and then like non-uniform weight has been used in a lot of other in a situation, for example, the like manifold learning stuff has been used a lot. All right, so and you can see like even with the k nearest neighbor, very simple models, we still have a several many like hyperparameter need to be tuned, and of course the most important part is actually the number of the neighbors to be chosen from. All right, so let's see. This is the scikit-learn's k nearest neighbors classifier. It has a bunch of options that you can choose. For example, the uniform, and that means all the weight have to be equal for those k nearest neighbors, or like distance. So like the weight is actually inverse proportional to the distance from this examples, which is also very popular as well. So, and because if the point is further away, so the weight will be smaller. And also the way to perform this k nearest neighbor, the algorithm is also very interesting. So as I said, this like, and the local sensitive hashing is one of the methods. But you can do, and there are, a lot of ways. For example, brute force. You can do ball trees, KD tree, and some other method like automatically. For this brute and the brute force is basically the nearest neighbors for each test cases that computed through this grid search. So that means it could be very, very expensive. That means like to find out the k nearest neighbor that you actually need to exhaust all possible distances for that point to all the training data set. However, on the third and second one, the distance between that, is actually stored in a tree. So you can like finding out the nearest neighbors in much more efficient way. So and by doing some search on the tree, and one of that is KD tree, and another one is ball trees. So it will be very efficient to search that. But of course, like constructing these trees will be slightly more expensive. All right, so and you can change this metric as well. There's a lot of metric you can change. But the whole point of the whole thing is we want to choose this main parameters. So we want to ensure our like learning algorithm is able to generalize into those unseen data. Because usually we cannot check our model performance immediately for those like true test data. So one way, so we are going to, and we did, as I think I spent quite a bit time in the last couple of videos to say I'm going to sacrifice basically a small portion of the data set to check the quality of the models. There are two possible ways. I mean, it's no harm to reiterate the whole idea. So the first things you can do, like hold out set, that means you are going to just hold out maybe 20% of the whole data set. Then train your whole models on this 80% of the original set. Then you're going to compute the performance metric on these models on this holdout set. I mean, this is usually being used and a lot in, I mean, when the data set is really large. So like holdout, set is being like used and discussed a lot. So for example, if we want to work on very complicated models like neural networks, that's the only thing that we're going to use. Like holdout method is being used a lot in those kind of most complicated models. Another one is cross-validation. So cross-validation usually works on read and a relatively smaller data set. So in particular, it's the k-fold cross-validations. So the k-fold cross-validations is this whole model is going to be trained this k times on a different k minus one subset, and check on the remaining like subset. So basically, and for example, we're going to split this into five-fold, which is 5 and 5 subsets, and and you're going to train this 4 subsets right here, and verify the remaining subset on this like red and the red part. So and you are going to do this and like round robin fashion. So you're going to reshuffle that, and these 4s will becomes training, and now this part will becomes validations. So then you're going to run this all 5 times since we're doing 5-fold. And for each fold or each run, you are getting the validation error. And then you get 5 different validation error. Then you're going to average this 5 validation error to be averaged validation errors for this k-fold cross validations. So this will be your model assessment. So as I said, it's usually averaged to give a like overall average quality of your problems. Cross validations and usually give a better assessment, and a k-fold and cross validations usually give a better assessment of this model qualities and compared to the hold and hold out set approach. I mean, obviously this is and pretty obvious because hold out you can only think about it. We only did for just one run, right? So we only did for one run right here. That would be just equivalent as holdout. However, and k-fold is we did a much more thorough ways to check for each block of data set. In fact, each block of data set right here has been used one and only once for the and validation data set. So you can see like this is very thorough way, and this like testing is very thorough. However, and you can see the disadvantage for doing k-fold that will be computationally more expensive. I mean, since we are doing this like k times, if we have a lot of data, this could like significantly increase the cost of the calculations. And also, cross-validation is also a very important techniques in this like machine learnings. It can be applied to the statistics and other stuff. So you can using this whole idea to do like hyperparameter tuning, model compression, and a comparison and the feature evaluations. Because And what you can do is you can choose one specific type of parameters. You run this 5 times. You have averaged validation error. Then you change this hyperparameter again to another value. Then you run this k-fold again. Then you have another the average validation error. So you're going to compare with the previous one to see and which one is better. So you can choose the best hyperparameter tunings by using this k-fold cross validations. But there's a warning sign here because for each hyperparameter that you choose, that you have to do this k-fold and cross validations again. So that means that could be really, really expensive if the data is really, really large and you have a lot of hyperparameters need to be searched. I would suggest if you work with so if you work with the one specific problems, I will suggest you to just run k-fold cross validations once for one specific parameters to see how much time that you actually needed. This gives you some idea and to test whether you can afford such kind of k-fold cross validations for hyperparameter tunings. All right, so very quick and review of this k nearest neighbor. It's very simple to implement. It's very well studied. It's a baseline for classification regressions, even with the recommendation systems. It can be adapted to like a lot of problems by choosing the metric or kernels, for example. So like as I said, the metric to calculate distance could be changing all along. In fact, you can using even like a kernel method to find out what is the best metric that you can find. This could be some similarity operations for those very complex and objects as graphs while keeping this like k-nearest and neighbor approach to be the same. So basically, you can change all sorts of different metric, and some metric could be very, very complicated, and even using like kernel method to do any kind of approximations. And also, this also usually give a very good interpolations, but this has some exceptions. For example, if the number of neighbors is really, really large, then interpolations may and deteriorate. And for examples, we didn't give him a loan because he is similar to the other 350 clients of 70 are really the bet that is 12% higher than the average of the data set, which usually it's not a really good idea if you choose k equal to 350, because that could that could be the problem of the the group populations, and they belongs to some like subgroups of the populations. This subgroup and the subgroup of the populations may have like higher like default rate, which and that like doesn't reflect any situation for that specific individuals. So that's why if we choose k is really large, that kind of like interpolations may not be reasonable. And also there's a lot of like disadvantage. For example, the model that we actually consider, and consider fast in comparison with and other compositions of algorithms, but usually and this number of the neighbors used for the very complicated classification problems could be like 100, 150s in realistic problems. And if we choose k equal to 100 or 150, in terms of speed, so it will say, decision tree could be even better and even faster to operate. If a data set has a lot of like variables, it will and also be very hard to find the right weight and to determine which feature is more important and which feature is not important. And of course, we need to transform this data to standardize the data, but that didn't address which feature is more important and which feature is less important, because sometimes we are just trying to combine all sorts of different features, but we are just blindly assume each feature has basically the same weight. And also, it actually depends on metric that you choose. By default, we will choose the Euclideans, but sometimes it might be a good idea to choose other kind of the metrics. And you can find these kind of good solutions of the metrics by searching over the parameters, but this could also be very, very time consuming to find out the best possible metric as well. And also, there's no theoretical way to choose the even considered good number of the neighbors. The only thing that we can do is we can only do the grid search. Basically, this is almost true for almost every hyperparameters of all machine learning models. And also, if we work with very small number of neighbors, 1 or 3 or 5, this method is usually very sensitive to outliers. If we have an outlier somewhere, it will be very sensitive to those outliers. So, in this cases, the small number of the neighbors, it actually reflected to the regions of overfittings. So if we have a very large number of the neighbors, this is more the inclines to underfittings, turns out, because that's more and more like a population's accuracy, and rather than to this individual accuracies. So this is something that you need to keep in mind, and this is also very frequent questions asked during interview questions. And what is the whether the small numbers indicate overfittings or underfitting in k nearest neighbors. And also, and it doesn't work very well if we have a lot of features, as I mentioned, because it has an issue of the curse of dimensionalities. So let's run a very simple data set, and that data set is the a telecom churn data set. And let's just see and how this k nearest neighbors performs. So in these cases, we are going to get rid of this state, because state doesn't I'm basically a categorical data set. We are not going to measure the distance between the categorical and the data set. We only work on the numerical data set. So we're going to drop this state feature for now. And we're going to work on the k nearest neighbors. So you can see right here, and everything now here becomes all numerical values. And I turn whether they have the international plans, yes or no, becomes 0 and 1s, so they can do some comparison here. So what we do is we're going to do the common ones, and here we're trying to do 70% of training and 30% of testing or validations. I want to emphasize this test data will not be involved in tuning the parameters at all. So that means this 30% of data will only give you the measure of the performances of the models. So it will not be used in hyperparameter tunings. So we will use at the end after tunings to assess the quality of the models. So that means we're not using that at all. And if we use that, we only use it once. So, and we are going to using two models, and decision trees and also k nearest neighbors. So and also we don't know and what parameters are good. And so we assume we just choose some random ones. And here we choose the tree depth is equal to 5, and the number of the nearest neighbors equal to 10. So this is a very simple test right here. So this is the trees. Decision tree, this is k nearest neighbor. It actually fits. So before we do anything, we need to do some standard scales. So it's like to transform the data. So we transform the training. We transform the testing. There are very, very important part that I want to emphasize here. I think I give some ideas in the last couple videos. If you want to rescale the data here, for the training data set is you are going to train and fit this scales and scalars using the training data set. That means a scalar dot fit transform of X train. So for this, what does that actually did is they will fit on the training data set, then transform the training data set into X train scaled. And I want to emphasize this right here. You cannot, if you do this scalar dot fit transform of X test is wrong. So you cannot do that. Because if you do that, this scalar will be that we define right here will be retrained using the X test data set. Then going and transform into X test scale. Because usually this X train and X test has different means, have different standard deviations. So that means once they do this fit transform for this scalar right here, the mean and the standard deviation is fixed. That means for the X test data set, you are going to apply the trained mean and standard deviations and transform this X test into X test scale. So that is the correct methods, but this is completely wrong. In fact, it will create the biases. So this is very important. Okay, so you do the fittings. K nearest neighbor fit the so X train scale and the Y trains. For decision trees, you don't actually need to do any kind of transformation because they don't use the scale of the data. They only make the split for one specific features. We're going to talk about that later on of the courses. So we can do this kind of assess. The way that we can do is we are using the simple accuracy scores. And you can see right here, this decision tree give me 94% of accuracy. And K nearest neighbor is getting 89% of accuracies, okay? And I want to emphasize this and result is achieved by some picking random parameters. We didn't specifically do any kind of cross validations. So what we do right here, and I want to emphasize we're only using this testing data set once, right? We only use that once, and we only use this test and X test and scaled once to make any kind of predictions. Okay, so this is really, really important. I saw so many people make that kind of mistakes. If we see, if I see people who make that, mistake in the homework, that is automatically a red flags. Okay, so don't make such mistakes here. All right. So let's do some cross validation to find out the best parameters to tune for this maximum depth of the entries and the maximum number of features to be used at each split. So basically, in terms of the tree, there are two possible parameters that we can tune, and we'll talk about this later on. The first one is maximum depth, and another one is maximum feature. So you can set the range that you are interested in. Could be like, and here is 1 to the 10. This is 4 to 18, and you can set any kind of the range that you'll be interested. But you have to be careful. You can't just set these parameters too big and the range is too big, because it would take a lot of time to actually do this kind of k-fold cross validations to do this kind of grid search. Because for each set of parameter, you actually need to do this k-fold cross validations for each of that. So basically, they will just do this search and for each pair of the maximum depth and the maximum features. So if you do that, so here you can see, so for total possible maximum depth, that would be 10 possible, and the maximum feature that we have is 15. So, and it's in general, and there will be 150 candidacies of these three parameters. So you're going to using this grid search cross validations. You're going to plug in, okay, I'm going to, and using the trees, and you're going to specify these three parameters right here. These are the two parameters you actually need to be tuning here. CV equal to 5, that means my cross validations, K equal to, and so K fold cross validations is actually equal to 5, and that actually gives you how you are doing here. So that means we are trying to fit fold for each of 150 candidacy of the parameter. So in total, you are going to fit 750 fits. That's a lot of fit. If you have a lot of data, it would take really a lot of time to do that. So once you do this, you will find out the best parameter set is given as this right here. Maximum depth is 6 and the maximum feature is 17. You can see the best scores in terms of cross validations. You actually get 94.3% of validation accuracies, right? So, and what is this best score means is under the best parameter with maximum depth equal to 6, maximum feature equal to 17, you perform this 5-fold cross validations, and you calculate the average validation scores, and out of 5 fits, this is the average value is 94.3%. And of course, you can test with this Y test data and X test data. You are getting 94.6%. With this search, it actually boosts this entries scores from 94% into 94.6%, 0.6% increases. All right. Then what you can do is you can do similar things for the k nearest neighbors. But for the k nearest neighbor, you are going to do something that is slightly more complicated, because we have 2 steps, right? The first step is the standard scalar. We need to do this like data normalizations. The second one is after that, we're going to apply the k nearest neighbors. So the parameters, so we're going to use is k is from 1 to 9. So here what we do is we're going to create something called pipeline. So the pipeline is, you can think about it as a two block of like and a data processing method. The first block is actually a scalar, and it's called scalar. So we name this as scalar, and the actual function is being applied. It's called standard scalar. The second one is, that block is, call this KNN, and I'm going to specify, this is K nearest, K neighbors classifier from the scikit-learn. If I want to specify the KNN's parameters, this is the method that we need to follow. So you're going to call this name of that specific modules you are interested. So that would be KNN right here. We have a double underline to indicate we are going to modify the parameter for this K nearest neighbors. The parameter that we want to modify is n neighbors, right? So this is actually the parameters in this K neighbors classifiers. So you have something in your mind how to using this kind of pipeline to make and to tune those parameters. And of course, right here, we're using standard scalars. We don't have any kind of parameter need to be tuned. If you want to work on much more complicated transformation, sometimes in the scalars, you also have some parameters need to be tuned or trained. So keep in mind, it's very common. And also that's the method or the syntax to specifically tells the Python which part or the modules that you want to do any kind of the hyperparameter tunings. Okay, so and otherwise it will be the same. So you're going to, instead you plug in the K nearest neighbor, you plug in the K nearest neighbor pipeline. This is the parameter, you have cross validations, you do almost everything the same, okay? But in this case, it's like slightly easier because right here, we only have 9 candidates, right, from 1 to 9. And for each of that, you do 5 folds. In total, this will be 45 fits. As a result, you find out that the best K nearest neighbor you're getting is 7. And as a result, the like validation error you're getting is an 88.6. But however, if we do the testing data set, you still get 89% of testing. So like doesn't improve at all. So yes, we can using that kind of cross validations to pick the possible or the best possible parameters on this validation data set. But I want to remind you, validation data set is still an approximation of this generalization error. If you don't have enough data, this is only a good approximations. To ensure to pick the best parameters, actually get the best and the validation error doesn't necessarily say my test error will be even better, right? So that part is, and there's no guarantee. This even has a possibility that you choose the best parameter in this regions you apply into testing data set, you saw the accuracy actually drop. This happens a lot if your data is not many, like 50 or 40 data set, and this actually happens a lot. But as you can see, and right here, the data is only like an 89% of accuracy. It's not that, that impressive. Okay, so and of course we can see this tree is doing better than the nearest neighbors with the cross validations, and in fact we can do this like random forest if we want, which is much more complicated. It's and a much like and a lot of effort. We're going to talk about random forest later on. So this is the random forest and forest, how you define that. So basically, this is 100 and base estimators, and then this is you're going to fit that. So you're going to and directly using this cross validation scores to calculate and the validation errors for this like random forest. So you have a forest, you have a training data, you have Y train data, and the target variables. You are going to say I'm going to work on 5-fold cross validations. So basically, yeah, and since there's no like hyperparameter tunings, this cross validation scores will just simply output the average validation error for this 5-fold cross validations. Oh, sorry. That will give you 5, like, and you do this 5 fit for and for this 5-fold, you are going to output this five validation errors. So, and that actually give you 5 values. Then you can do this mean of that to actually get the average of the validation error for this 5-fold. Okay, you can do this things. Then you can do this grid search for the random forest. And I mean, so even with the random forest, they will be getting even better performances with actually getting like 95.3% of accuracy, which is pretty good. In fact, I mean the cases, and compared to like what we already have for like as a K nearest neighbor, you are getting like an 89%, but with the random forest, you are getting like 95.3% of accuracy, which is quite impressive. So I'm not going to run this because that would take a really long time to run, and I would suggest you to go back home and run it by yourself. Okay, so I mean, so in this case, I'm just like trying to demonstrate the K nearest neighbor is and tree is better than K nearest neighbor. But let me try another data set. It's quite real and a realistic data set. You will find out K nearest neighbor is, I mean, could be doing very good jobs. So right here, you see this is the handwritten digit, but this time, I mean, this is not the exactly MNIST data set, but this is 8x8 matrices, right? So this is not 28x20. It's like in a simplified version of that. It's 8x8. You can see this is the image that we're getting, 1, 2, 3, that we're getting here. And then let's just do this 70% and 30% split for the training and testing that we already have did that. So I mean, it's almost the same thing. We do this student tree and K nearest neighbors on some random parameters. I think we have a random depth is 5, number of neighbors 10. If you do this testing right here, you're getting really good and a surprising end result. K nearest neighbor actually getting 97.6% of accuracies. But I want to remind you, this is random parameter right here. And the decision tree, you only get 67% of accuracy, which is not good at all. So we can tuning these parameters. I think still like pretty quick. You can tuning all these different like maximum depth, and maximum features. So you do this performances, and the best parameter and the best score you're getting here is 85. So this is not really good because a random like parameter for K nearest neighbor, we are already getting like 97.6% of it, the accuracy. All right, so you can see this is my K nearest neighbor is doing much better job. I mean, if we want, we can even using the 1 nearest neighbors, which you are getting almost like 99% of accuracies. So really good. You can see. I mean, so if you choose like n neighbors, you do 1, to do this cross validation scores for this 5-fold, you are getting 98.6%, 99% of accuracies. And I mean, in fact, you do like random forest on the same and the data set. But usually random forest is doing better on the k-nearest neighbors. But in this cases, random forest is only getting 97.5% of accuracies. On the other hand, the k-nearest neighbor with k equal to 1, this is considered the simplest possible methods, actually getting much better. So this is something called, and you can, I mean, this is something that is something called like no free lunch here. That means there's no universal method can work on an arbitrary data set well. Sometimes that simple method, k-nearest neighbor with a k equal to 1, can getting 99% of the accuracies. And I mean, in terms of the speed and everything, it's also very quick. However, compared to to the random forest, and the random forest is usually slower and much slower to train, much slower to inference and to test, and turns out the score is even less than the k-nearest neighbors. I mean, here we and we haven't tuned any parameters for this random forest, so we just pick some like random parameters. But if we actually do this kind of like hyperparameter tunings, you are even getting more than 98% of accuracy. Still, k-nearest neighbor give you the best result. Right here, and let me show you one more example. Actually, it's a very simple example. That k-nearest neighbor actually fails. So here we're going to create the noisy data set, and one of the feature is just proportional to the vector of the responses and the responses. So basically, your y is basically it's the first feature that you got is just proportional to the target we and what we want. It's very simple, and everything else is just being noises, right? So that's a very simple data set. I mean, so from how we construct that, that means only one feature is actually useful. Everything else just a noise. But of course, it's whether it's k-nearest neighbor or random forest or like decision tree, they don't know that. And we want to see which method actually give you and the best results. Okay, so we do all the things. So you can see, and this is basically the the routine that we have. And we can see the result right here. So you can see with the k nearest neighbor right here. So you can see as when the k is getting like bigger here. So you can see it start to like increases, right? And the accuracy start to increases, but never reach like 100%. However, our like and cross validations and actually start to like and wiggle and start to drop off, and at the same time with the testing data set, it start to drop off here. I think sweet spot is I think it's about 300 right here. But I think you are getting like 98 or 99% of accuracy. But you can see this is and doesn't do very well because this is such simple and data set. Even you vary the number of nearest neighbors, and didn't like capture the way that to identify. The first feature is actually the most important features. But however, we can using and it didn't trace, and even with one layer, just one single layer, you can perfectly separate the data because the and the didn't trace can immediately find out the first features is actually the most important ones. All you need to do is just split on the first features, and then you will be done right here. Then with only like and maximum depth equal to 1, the cross validation and holdout all reach to 100% of accuracies. So this is the simple cases that actually k-nearest neighbor actually fails. However, the entries can easily detect what is going on here, can find out the best result for that. Okay, so this is basically a simple overview about the k-nearest neighbors. And also the most important thing is we're using this whole idea together with the decision trees to give you some idea and a starting point to and to tell you how to build models naturally and how to process the data and how to using cross validations to hyper tuning those parameters. And also very important part, we also demonstrate a very simple pipeline and how to using pipeline and is at the same time to using the hyperparameter tunings, right? So this is, this lecture, so k-nearest neighbor is not the most important part. The most important part is we are using those kind of and the whole procedures. You need to learn this whole procedures for the for almost every possible models right here. So here, we're just using k-nearest neighbor as examples. You can easily change this k-nearest neighbors into logistic regressions, and everything here will be the whole skeleton of the code will be almost identical, but you just change this k-nearest neighbor into logistic regressions instead. Right. So this whole thought is much more important, and this whole thought of the processing the data is much more important than which model you should be using in this and right now. And also, I also emphasize one thing right here. And for the scaling, you need to make sure you only train your scaler on the training data set and apply your scaler on the testing data set. You never ever fit transform on X tested data set because that's wrong. You are retraining your scaler, and so if you do that, and this scaler and this scaler will be two different things. Okay, this actually create biases, and I see so many code is doing that. As a result, their accuracies is not correct. So their accuracy scores will have some biases here. All right, so that's everything I want to talk about for this video. Thanks.